I hope everybody had enough coffee. Actually, I got 2 cups myself, so I'm all caffeinated up. My name is Jignesh Shah. I work at AppOrbit. We are kind of designing and redeploying dev and test environments for your production environment. Prior to AppOrbit, I worked at VMware and Sun Microsystems. I had a lot of work with various Postgres benchmarks and getting Postgres working on virtualized and cloud infrastructure. Josh and I were together at Sun Microsystems for a period. So I started working at Postgres in 2005. And actually, I've also been working with containers, it was called as Solaris zones as one of the forms of containers which was available in different Unix, right? So containers are not new. I think the adoption is new for Linux, but it has been there for a while. My clicker works. Okay, cool. All right. The agenda for today is we'll talk about containers. We'll talk about Postgres replication, high availability of that, and what does it take to do and deploy it in enterprise environment. Before that, how many of you are using containers? Roughly about 50%. Okay, cool. All right, so let me do a quick stab at what are containers. So how many of you are aware of virtual machines? Right, okay. So the difference is virtual machine works as a hypervisor layer, which kind of abstracts out the virtual machine. The way containers are designed to work, they actually work within the OS, so you kind of share a common kernel across them, and everybody gets an isolated user space. So I think that's kind of the key word out there. What you're really essentially getting is your private user space, right? In some cases, like people would say, how different is that from like a group of processes? You kind of isolate them. Yeah, they're pretty similar. But I think what is happening is like you now have better isolation that you can do across these groups. And it all started with C groups forming that base of giving you control groups for a group of processes where you can actually set up different resource limits for your set and do a finer grain of control out there, right? So that's kind of like the details. Like, let's look at what the advantages that we have, right? So what I've talked about is traditionally things have been all bare metal. Then the wave of VMware came, which was all virtualizing your infrastructure, so everything was VMware. And then came in this container wave, which is now kind of like somewhere shifting between some people would say, hey, put it and run it directly on bare metal. And then there will be a group of people who would say, hey, they will all work in coexistence with VMs also. So you could do kind of like a nested layer out there, right? Personally, I don't care how you use them, just use them, right? I think I might have to stand out here. Okay, so the advantage of containers that we generally have over VM is the lower footprint, right? When you kind of do a virtualized machine, what you are doing is like you have the whole OS instance running. So the kernel is actually replicated every time you kind of boot up a VM. What container now allows you to do is take up a lot of your smaller services, and you could now actually package them kind of like a light VM and run them in a single instance of the VM. And that way you get more bin packing to be done. So the advantage you have is like you now have a smaller footprint unit that you can do, which is faster to deploy, better to manage, and you could actually kind of if you look at it, what happens is they're faster to kind of roll up, scale up, and scale down. So the time it takes to kind of spin up a container is actually way smaller than what it would typically take to boot up a VM, right? But there are disadvantages. The disadvantage is pretty clear. The VM, the advantage you have is you can run any operating system. It doesn't matter. You run Windows, you run Linux, all on the same infrastructure, it works. In container, your base platform still matters. You just cannot take like Windows and run it in a Linux host. So that's kind of like I have this question many times, like, hey, can I run like a Windows container on Linux? or a Linux container on Windows, you cannot, by the pure container technologies, what people have done is they have created lightweight VMs in a container sense that would allow you, but at that point of time, you're still running virtual machines. So by design, you're sharing a common kernel. What you can do typically is you're keeping the same kernel interface for your applications. The good thing about Linux, which what we are doing a lot, is Linux gives you a uniform Linux API. So it doesn't really matter what distros you run within them, but it still has to be a Linux-flavored machine, a Linux-flavored container that you would run typically. So if you are planning to use like Windows containers, you still have to use Windows base OS as your container host. There are other things that you do not want to do is security is still tied, kind of different compared to virtual machines. It's getting there, but there are not strong isolations even available right now. I think there are a lot of enhancements happening, but it's still not there. So those are some of the things that if you kind of worry too much about security, you may still want to stick to bare metals if you want and kind of keep them under your desk, not connected to the internet. That would help out quite a bit. But I think what we are finding is like the way the whole world is going is all your personal information is on the web anyway. So, people want to go to the web. So that's kind of what will happen. So this is some of the interesting things we'll see. So just to kind of like refresh, what we do see is because of the faster ways to kind of deploy, the best ways to think of it is our containers are now more and more becoming the cookie cutter images that you deploy out, run it. When you get done, you kind of pull them back. If you have newer images or new updates you do, no longer you kind of run an installer upgrade on your setups. You kind of just wipe out your container image and replace that with the newer version of the whole container image containing your software. So it's kind of like causing the shift in the industry. People used to spend too much time in getting their installers right. Now what they do is they try to make that data and APIs backward compatible, so when you swap the binaries, you actually can still work and upgrade the database out there. So that's kind of like doing some interesting trend out there. If you have never tried out container, it's actually pretty easy to set up. All you need is like a Linux host. Add the repository, which Docker is graciously hosting out there, and you just do yum install Docker engine. For a typical experience, right, in the old days, if you need to run a VM, first of all, you needed to have Intel processors capable of running VMs. Then you need to make sure you have high enough memory to kind of spun up like a Windows machine on top of that. I think it was like the barrier to entry was pretty high. Compared to that, containers have become quite easy. You take a laptop, you do yum Docker install, and you could actually be running Hello World pretty quickly, like within 5 minutes, without really too worrying about, do I have the right resources or not that. So like I said, hey, we are in a Postgres conference, so we should probably, what we want to do is actually run Postgres in a Docker container. How easy is it to run in a Docker, Postgres in a Docker container? Compared to the old days, actually I started in 2005. My first experience of Postgres was to download the source code. I needed GCC to install, then run the configure script, then do a make install, and then finally I had a binary that I could use. In today's world, you install Docker, and you directly say Docker run Postgres, and you just pass the username and password that you want to set for that configuration, and whoa, you actually get a Docker container running Postgres that you can now connect to it. I think what you see from this is the agility that it is actually now providing to the community or in the world in general is like you will now see a rapid spin of new product adoptions which are now kind of made easy to use, right? Because what you now have a standard shell container, if you have designed your product right on how you want to use it, you no longer care about what the environment looks like. You are living in your own shell, you have designed everything on how it works, and you just say, hey, just run this container because it's guaranteed to work out there. In the old world, I'm writing an installer. I'm going to run on Linux 7.2, but my customer will have 7.1, and I think I have to do a lot of worries about, am I handling all the cases or not? It was a huge concern. I think a lot of these things will go away because the way people would do is they would run a container image, which is fully self-sustained within the image. You may still have some glitches depending on the Linux OS kernel version, but Linux OS kernel version recently has been quite stable. In fact, in many of the tests we have done is you actually run multiple Ubuntu versions on the same Linux kernel, and they all work together as containerized images. So it has given power to people to kind of do a lot of new things which were not possible previously. All right, now I think kind of shifting a little bit from container to Postgres, right? I'm talking about running Postgres in containers, but it's not easy just kind of say, hey, I'm running a Postgres. You can do your dev work and everything out there pretty fast, right? But you now have to understand how do you kind of manage the database when you're running within a container. Because if you one of the things you have to remember, containers are designed to be immutable, right? You kind of create an image, you run it, and then at the end of the day, you should be able to just destroy it without actually deleting anything else. So what do you do about your databases? So I think the thing to run is what you have to now start learning to kind of keep your application binary separate and your data separate, right? So if you look at the common paradigms of how containers are used, you run your application inside a container, but your data will be then mounted to that container, and it will operate on top of that. So the most popular version out there is Docker as a container engine out there. So what Docker you would do is, even when you run the Postgres engine, in the earlier example, I didn't specify any volumes, but inherently it will create a volume for your database that you should be able to kind of shut it down and reuse that volume somewhere else. So the data is now persisted in volume. So if you want to remember, how does the container tie into your actual disk? It's called volume. The volume part of it will help you to kind of put your database into volumes so that when the container dies, your volume are persisted. So this, in essence, is the persistent story of containers. There are a lot of different examples I've given up there, but in the interest of time, I'm going to go to the next slide. The other thing you need to do is, we have talked about volumes, but how do clients connect to it? So in containers, what you have is a basic networking mechanism where you take the container ports and map it to your host ports, and that's the network plumbing you have. So we've talked about volume. The next thing is networking. So the -P options in that gives you an ability to say, map your 5432 port of Postgres to any of the ports out here, so that when your clients connect to it, it will be connecting to at specific ports, right? So now we have learned about two things, volumes and networks. Now, the next thing we want to do is also kind of limit the memory and other things, right? A lot of people come from VM backgrounds. Hey, I know what my database hardware resource requirements are. I want to set up memory and CPU requirements. You can do that with Postgres too, with Postgres running in a container. Containers, at the end of the day, are C groups. C groups allow you to map, put limits on the CPU shares and the memory. In some of the later versions, you now have ability to map CPU sets to a container, so that kind of gives you kind of the hardware isolation. You can set this particular NUMA group are dedicated to this container, so now more and more you can actually get some of the benefits out. Newer versions of that will also be doing more fine-grained resource mapping out there. So there are a lot of those things you can get out of the box now with containers. Typically what happens is, this is kind of an amazing experience. 2005, when I first ran Postgres, the first thing I ran is when I bump up my shared memory, I ran into a problem. The kernel Unix memory wasn't set up to give you that big shared memory. Same thing will still apply out here. So even if you're running in container modes, right, your kernel limits needs to be higher so that you can allocate bigger shared memory chunks if you need. A good thing is with the latest version of Postgres, it now uses POSIX way of mapping into the shared memory segments, so you don't need to kind of bump any of the kernel settings. But if you're running any older Postgres versions, you will still have to do that. If you use Docker, Docker gives like a shared memory settings for your containers, which would allow you to override the kernel values out there. So that's kind of something that you would see out there. Now, there are some of the things that you often say, right? People are hard-tuned to kind of separating out their Postgres logs into different disks and some things like that. So those things are still possible. But in order to kind of do that, you would need like a customized image of that. So like one of the things I say is like, typically Docker gives you like a starting Postgres image. If you kind of run off-the-shelf Docker images. But if you are going to deploy in your production environment, you need your own custom image. The custom image are basically based on the requirements of an enterprise. It could be the versions, it could be specific extension packages that you need in Postgres, it could be related to like what your backup strategy is for your archival and other things, right? So what we typically end up doing is create a customized Docker image, and that we kind of use it out there. Now comes the real topic, right? This was all introduction, like what do you do to kind of make Postgres run inside the container? What are the key caveats that you need to be aware of, right? Typically, when you want to put something like this in production, the first thing people say is, hey, here's my list of requirements. Do you meet this? How many people have actually seen this, right? People would say, I need 5 nines. Then you talk about them, right? Like 5 nines is literally like 6 seconds downtime. Sometimes my DNS server doesn't give me the record in that time. It happens, right? So this is a common thing. This is what the management will tell you. You have to kind of figure out like how do you kind of get to there, right? This is our goals. And one of the interesting points that I always say, right? There are 2 key metrics to do. And the way they're conflicting of each other. There is recovery time objective, which means says like how fast can I recover? And there is a recovery point objective, is like, how much data loss do I need to be there? If you kind of try to do both of them, they are kind of countering. Like if you try to get one right, the other one goes away. If you get the time right, then you're losing. So there are trade-offs that happen all the time that you need to be kind of aware, like what are the right settings to kind of meet those requirements, right? Thanks to Amazon, here is the management view of a highly available Postgres setup, right? What Amazon says is, here's your DNS name, and here is something somewhere running in the cloud, which is highly available. And that's what the management expects. Now, this is kind of hard to do, right? It looks good on paper, but when you actually try to do that and implementation in your own enterprise, it's actually very hard. Because the first thing that you say is like, you have planned downtimes. Like half the time, your downtimes are not unplanned. They are actually planned. You're going to do software upgrades. You're going to do schema changes. You're going to kind of upgrade the servers. Like, most of the time is like, oh, I'm running out of memory. And people would say, oh, I need to shut down the server to add more memory and then boot it back up, right? I mean, that's why you use VMs too, so you can vMotion them out to a different server directly. That was like one of the big selling points of VMware. Then the second thing now people are trying to do is like, oh, we need to take them to the next whole level. I don't even care where I run, right? All I need is that service to be up and available. So there are a lot of reasons why things can go south. At the same time, a lot of people are doing like some of the standard things, right? If you work with Postgres, you kind of try to balance out your checkpoints. You try to elongate your checkpoint good enough so you get performance out. But the downside of that is like if things crash, the time to recover that database itself will kind of throw your SLA out, right? If you are recovering with a 15-minute checkpoint, right, it can take anywhere from 5 minutes to 7 minutes to completely restore from a database once it crashes. So a lot of time, if you kind of nitty-bitty on what is downtime and uptime, you will find like a lot of the settings that you select by default can actually not even allow you to meet those requirements. So what do people do? They actually change the definition of downtime. So downtime is not the part when the DB is not available, but when the DB server process was actually down. So people do funny tricks on how they define the downtime. So it's kind of things. But still, there are a lot of things. Like if you look at the classic enterprises, their first story of HA was shared storage. To be honest, that is still true, even in the container space. People are still using shared storage as a way to make sure they can do fast recover. The simplest way of HA. Typically, you would still see them in enterprises, but not in the cloud. Clouds, it's hard to get shared storage. The most common shared storage in cloud is NFS. People do run that as a way of shared storage in the cloud. But in enterprises, they do have a lot of Cisco networking gear with EMC storage out there that you would commonly see, which they say, hey, I've already paid for shared storage, I want to leverage that. So those are still good ways of using it. So the first kind of paradigm that you would see out there is like, even with containers, people use shared storage that are common in enterprises because they've already paid for it, they have it. Container, because you have already separated out your volumes with the data that goes into shared storage, you can mount them dynamically on your clusters anywhere as the set of pools that you are designated out there, so you can remount them. And containers are very easy, right? If you kind of like fail on them, you can actually automatically orchestrate that to kind of mount the volume on the other side, start the container, and it picks up right from that point. So that's kind of like one way of doing HA that still works. It has its own pains as such, but because shared storage by nature is very expensive, so it's not something that most people would go directly for that, but if you have that, that's still a valid way of using containers, high availability story. Now, we are in a Postgres conference, so we need to talk about Postgres application. So Postgres application is another way of doing this. The benefits of using Postgres application over shared storage is you actually get full copy of the database. So even if you have like a block corruption and other things that happens at the media level, and using Postgres replication, you actually now have two real copies. So you are actually saved from those kind of bit errors that you would typically get. The second benefit the Postgres application gives you, which a shared storage cannot give you, is read scaling. So if you have a read-heavy workload, you can offload some of the reads to the slaves. And by having a multiple range of multiple reads slaves, you can now scale up your workload accordingly. So that brings up there are definitely benefits of using replication over shared storage. You get more tunable options. You can define whether you want synchronous replication, you want asynchronous replication, you want local replication, and you will have like how many nodes do you want in your replica set for synchronous, and how many nodes do you want as an asynchronous setup, so you get a lot of flexibility. So that's the second paradigm that you have is like using replication. So when it comes with containers, what happens is now you have two volumes to manage, or it could be n volumes, depending one for each node. So when you kind of do an orchestration, it doesn't really matter because every time you spin up a new replica, it will use a PG-based backup to kind of deploy the first copy of that and do that. Now, there is an additional thing that you could do. You could still leverage your shared storage, kind of to spin up new copies faster, so it doesn't have to start from zero all the time. So people have done interesting things out there to kind of say, how do you do fast spin up of slaves out there? So that you would see, right? So the number one problem with replication is all the things I told you looks great. I have so many choices. I have so many options. But when you try to kind of like say, what is the option that will work for me? Sometimes it takes like weeks, if not months, to get it right. Like, do I really want it? So that is one of the problems. The other problem is replication by itself is not good enough for the DevOps story, right? You do not have automated failover. You do not have failback. You do not actually have a way of kind of doing the load balancing or proxying between the master and the slave by itself. So what it leads to is you now have to get not just the Postgres replication, but like maybe at least PG pool or rep manager or handy wrap for some ways to kind of help you set up that replication and manage them. This is the point of time. If you talk with many customers, they actually stop at this point of say, I'm going with the RDS service or Heroku service because it's easier for me to just pay for that and get the high availability out there. If you're such a customer, please talk with me. We also do give out services like that. So I'll be happy to talk with you. But one of the things that now is actually coming along, and how many of you actually attend the governor that Chris and Josh did? Okay. And Josh's talk on Petroni. Nobody, okay, all right. So there are three more new projects that are coming, which are trying to help out in kind of filling this gap, right? So now you have this modern way of deploying applications using containers, and you have Postgres replication that you really want to use. So the way to kind of bring them together are this new kind of projects that are coming, which is called like Governor, and its actual fork is Petroni, but Petroni is like a completely Dockerized way of kind of deploying and doing your promotions and proxying all completely integrated with Dockers to be deployed out there. So the next question is like, how does Governor work? So I mean, basically what it is, it's a program that runs with every Postgres installation. When it starts up, it basically says, do I make this the master or not, depending on a status that it has. So they will all be kind of like doing like a config management of the various things that you have in your cluster. And then you would be able to kind of like say, the whole idea is like an autonomous deployment. Like when I set it up, let it select its master, let it select its slave, let it start up and configure it itself in a replication mode. And when things go something wrong on the master, one of the slave will automatically pick it up. This is actually very powerful, right? In the old days, what used to happen is master would go down, somebody would say it's not working. The next person, like the guy who is the DBA, will be given a call. He comes online, does this. What does he do? The first thing he will do is take one of the slaves, promote it, and say, I'll look at the problem on the master in the morning and go back to sleep, right? Very typical thing, because people, that's what they do. You don't kind of start debugging the live environment. You need to get the service running. So what they do is they promote the slave and go back to sleep, like, I've averted the fire, I'll look at it in the morning. Why not automate that, right? I mean, that's your number one thing. So this projects are essentially allowing you to give you that kind of capabilities. So that's kind of the powerful nature. The number of calls that a typical DBA will come is expected to go down significantly, because what you're doing is you're taking the immediate action that you would have taken anyway, which is promoting the slave, right? You have to make sure that the master is no longer available, which is taken care of, like the master would be then shot to death. But that's the typical action that people do, and now it's automated. Right? So Governor is kind of like the framework that allows you to do that, and Petroni is the fork that they kind of combined Governor along with Docker images and give you a full set of Docker, full functioning Docker image. So you say, I'm deploying 3 versions of Postgres. You deploy them. They will automatically select one of the guys as the master, the other 2 as slaves. And now what you get is a combined master and 2 slave replication. And they actually have a quorum, which is kind of maintained by etcd as one of the other clusters out there, right? So that's kind of like how the world is going. Like what they are having is a repeatable deployments that is doing a self-managing and re-electing the next slave. And then if things go south, with the master, a slave is there to pick it up, and it will send a notification. And when the actual DBA comes in, they will spin up a new slave and add it back to that pool. In fact, some of this notification can be used, received by orchestrators who would then automatically deploy a new container for you. So it can be completely automated. So it's kind of like the panacea that people are looking for. It's getting you a step closer to that, right? So governance, yeah.
What about in case of refrain mechanism?
So in this typical deployments, what they will do is they will always do in this kind of like a pack source way, right? But most of the deployments that we do is like you would do in sets of 3, and you would then increase them in a way that is kind of pack source compliant. So as long as there is a quorum out there, that takes over, everybody else are shut down. So generally, when you're deploying this in a single data center, you wouldn't see that many issues. And the algorithm takes care of most of the split brain issues that would typically arise as such.
Are they going to check the time?
They So those are kind of the enhancements right now. The logic is not really foolproof, right? It kind of selects the standby based on some of the previously mentioned lag data that it has, but it's not really foolproof as such right now. But it's still, it does check that, but I wouldn't say that's a foolproof thing. Like it doesn't always kind of get the best one. So we can go more in detail into that later on. I want to finish the slides. But yeah, so there are some caveats to that, but it does get you to a step which is a lot closer. Governor is not the only project out there in that scope. There is another project called Stolen. On a high level thing, it does similar things, but their implementation is quite different. They have their own proxy mechanism, so they can actually control who gets to what node also. So kind of like if you take the high level view, right, from both these projects, you can take out the common aspects of it. The common aspect is what people are now doing is, whenever they are deploying, they are taking the configuration data and storing it in a distributed data store. That distributed data store now becomes kind of like your source of truth on which guy is alive, which guy is the master, which guy is the slave, and how far behind they are. They all publish that data. And when typically each peer by itself is kind of self-managing, so there is no central controller as such. Every peer, when they boot up, they look at the data in the distributed configuration data store that you have and makes decision based on that. So typically what happens is, hey, when I come up, I'm publishing it. If nobody else is the master, I'm going to make an attempt as a master. If nobody else wants to be the master, then I'll become the master anyway. But if somebody else wants to be the master and they are the latest copy compared to you, they will eventually take precedence over you. But you have this timeline by which you need to kind of do that all this fine, which is where the caveat comes in. And then the first guy that becomes the master, then everybody now starts pointing to that one. If you kind of look at the number of steps that it does, it's kind of huge. But I think the way, if you look at it from an enterprise point of view, you have abstracted that problem to that particular core. And now your infrastructure is no longer dependent on doing all the job itself. Like promotion and other thing is now kind of orchestrated at that level, right? The other thing you would see in such kind of deployments is like there is a rise of usage of distributed key stores because there is a lot of configuration data that is needed to store, and you need a highly key value store that is kind of distributed and able to kind of cluster scale on its own, so it's not a single point of failure for your deployments. And there are actually various examples. etcd is the one that we are using for this particular case. There is console that is available. A lot of people that come from the Java land are using Zookeeper for storing such, configuration data, so that you have a lot of choices out there. At this point of time, I also want to kind of talk about some of the other trends I'm seeing, right? Now, we talked about how can you take a hard problem and kind of narrow it to a specific use case and say, how do I do automation on that to recover the master automatically, right? But then there are caveats. And the caveats are causing the new trends that I'm seeing. The caveats is like if you have done replication enough, right? You know that table spaces cannot be replicated easily because they need to be identical on the other side. The problem with containers is your volumes are fixed. you cannot add containers on the fly as such, right? So if you're creating a new table space which is going outside the container, there is a potential for you to lose data. So what that kind of leads to a behavior from the user point of view is like, how do I kind of minimize so the deployments work? It kind of doing some new trends. So the new trends that I'm seeing right now is people are moving away from table spaces. I don't know whether it's a good thing or bad. In the old days, I would always create like 7 or 8 table spaces, separating the index, separating the hot table, separating everything else. I could separate out, put them into different spindles and other ways. Those are becoming harder to do in this automated deployment world, where everything is now going to a one set. The other thing you would see is like, it's kind of funny, but many times I see the data and the write-ahead logs going in the same volume. Why is that? Because the way things work is you want them to be kind of like transactionally safe, right? If something happens, and if those are 2 different volumes going into 2 different things, and if you are using some sort of shared storage, and if it doesn't come up at the right consistent layer, then your database won't be able to stop, right? So like a lot of, and there are now a lot of distributed storage that are coming, where people are using fancy ways of doing copy on write file systems, where you want to make sure that they're all consistent snapshots across various volumes. So depending on your environment, some of the use cases I've seen is they put everything into one volume, which is kind of guaranteed when it comes out there, you have everything in that one volume and you can boot up and go ahead. So I don't know whether this will be true, but these are some of the trends that I'm already seeing that are happening that are kind of from the old days that I've seen of the database usage that is now slightly changing out there. And we already mentioned that replications and other things are happening automatic. The other thing I want to say is like microservices is the new buzzword, but I don't know how many people know the impact of microservices on databases. So one of the impact of database is with the microservices, like every microservice now has its own data store. What essentially they're doing is taking their bigger single database concept, breaking them into smaller and smaller databases where each microservice has its own persistence layer. And that's the way they are trying to scale those microservices out, right? If one microservice has a dependency on other microservice data, then they won't be able to scale. So what they are doing is essentially each microservice is a unit by itself with its own persistence layer. So that's actually causing another trend that I'm seeing is I'm actually seeing the number of individual instances of databases actually going up significantly. With every microservice out there, they say, I need a new database service for that, which is kind of like now constrained down to only that microservice, and it only maintains its set of data, right? So that's another thing. The other thing is like, we already talked about, like people do rip and replace of the images, the microservice versions at the scratch. So they are already designing the schemas to be some ways be handle of future proof and backward proof. So when you have to switch versions of your microservice, your data can be adapted to at least n-1 to n+1 kind of way. So that would help them to do kind of like fast upgrade, fast rollback if things go wrong, and so on. And a lot of times they would do is like they will have new microservice versions when they do that, and then deprecate the old version and slowly move ahead out there. So the trends from a database point of view, earlier I could go to a single database and I get the entire view of the enterprise. Now is shifting to a lot of smaller databases doing individual things. So if you want to kind of get a global DB view, you have to have access to all the databases and then see what's happening. So that is kind of like a fundamental shift. From a database point of view, I kind of feel like now I have to do that correlation myself. In the earlier days, I would see the database actually, there would be one large database. I know everything is out here. I know how to get other things from that once you have that. So that's kind of a trend change, but that's the thing. So going back, like how does this work, right? So now you have combinations of what we call about like a Patroni-based deployments with shared storage. There are a lot of features that are possible with that. So you talked about like shared storage giving you snapshots, recoverability features. Postgres application giving you read scaling and other features. And kind of like using Petroni, you are now getting the automated promotions and deployment features that can be hooked in. And life is good. But then, as I said, what's happening is like I am getting more and more database deployed. So now I am doing the same work multiple times because every database microservice you deploy now wants its own database. So the trend that you are seeing is like, okay, I need to do this now at a bigger scale. I need to deploy that same kind of things multiple times for different services that are running in the enterprise. Right? So now we need some other solution to solve this problem. And this is where actually Kubernetes comes in. So Kubernetes is a production-grade container orchestration. What I talked about doing at a single database level, I can actually do that at a bigger scale. By using a cluster of things, I can now start deploying various database servers and probably do my own kind of mini database as a service within my own organization. There are three kind of key pieces that are really helpful out there, right? I did mention like if an event at Petroni happens, I need to take actions. Like, do I need to spin up new slaves? So those event notifications typically would be taken by Kubernetes itself at this point of time, and Kubernetes will automatically provision a new slave for your deployment. So that will help you kind of making sure that the nodes that are going away are replenished, and you have met your SLA requirements on your production Postgres cluster size that you want to maintain. Another neat thing that Kubernetes gives you a hook to kind of do decision-based adding of new nodes. So you could essentially write up a small script and say, hey, if this read slave, if it reaches 90%, just spin up another slave. And you can actually do that, and you no longer have to kind of keep the monitoring yourself. You could write a small script, trigger Kubernetes to provision a new slave, and now you have increased your number of reads slave servers that you have on your setup. So this can be actually pretty much automated based on your rules that you want to apply for your deployments. The other common problems that you would have is like doing common configurations across all these clusters. So Kubernetes has something that's called config map. Config map allows you to kind of push the same configuration to your set of clusters which are similar in nature with various differences that you can have. So what you would essentially do is like you would take like a Postgres.conf, if you have a standard setup that you want to do. Like I have a dev test QA setup. I would define that as a config map, and depending on your deployment, I would say use the dev setup, use the production setup, and deploy it. So now you have abstracted your development and your actual production containers, and you are kind of mixing them right at the fly of deployment. So that allows you to kind of like scale very fast. No human intervention required. You set up rules and you can deploy them automatically. The other common things is like certificates, right? If you are deploying in an environment like an enterprise, it could be possible that your Postgres deployment actually has an SSL certificate that it will need to use to kind of maintain and work with the end user client. So there is something called secrets in Kubernetes that can be used for passing down the certificates that comes from your so there is, I'm assuming there is a key management software which tells you, hey, here's the certificate that you need to use for this deployment, which you can typically store as a Kubernetes secret, and that would be deployed for your environment. So now you basically kind of have fully automated where you pick and choose the configuration, the secrets that you need, and the environment, and say, go and deploy your Postgres environment, and that happens automatically. Now, few of the other things like I want to talk about is like, how do you kind of now combine all these things together, right? We know that there is volumes. We are now deploying Petroni-based setups. We are using Kubernetes to help us to do multiple Petroni-based clusters. How does the end user even know what to connect, right? So what Kubernetes gives you is a feature called external service. And I think this is important. Like you'll see the plumbing, how it goes up. The Kubernetes service basically says when you define a set of, say, we'll take the example of 3 Postgres nodes, right? There is 1 master and 2 slaves. You want a single entry point that can do load balancing. So if you have a read one, it should go to the anyone. But if I have a read-write connection, I need to go to the master. So there is a, Kubernetes gives you ways of doing label-based services. So you can actually create services based on a master label that Petroni can set, and then give you a Kubernetes master service where you can do read-write queries. And then you could also do a common service which goes across and round robins on all of them for your read queries. So that kind of allows you to kind of do that plumbing automatically. Now here's the beauty. Say for example, I'm running this containerized platform, and I'm running them on 5-node Kubernetes, right? And I'm actually running only 3 containers, which means essentially even if they have NT-affinity, they actually go into 3 nodes. What if the advantage of the Kubernetes service is, like once I define it, you can come to any one of the nodes and it will internally reroute you to the correct container that is running out there. So that powerful nature allows you now to kind of give you a feature that you can not only load balance on the Postgres slaves, but you can also kind of from your high availability point of view, you can point to any of the Kubernetes nodes in that cluster, and they will be automatically rerouted where the actual service is running. So from a client perspective, I can do a DNS round robin on top of them, and I can connect to anyone I get to my Postgres server. So this is actually pretty powerful. So that's what now we have. We have a Kubernetes-based deployment where you can do multiple Postgres server deployments around the world. Around in your data centers. They can actually be doing on different data centers also, or different geos. And you can set the rules, provision them, auto scale them, and so on. Now, when we go to the actual DR scenarios, people do mandate that your DR copy or something like maybe on across different clusters, right? So there are some things that you may still want to do is, you may actually take a warm standby and keep it in a DR site. If something goes south, you need to kind of repoint it to your DR site, right? So there are now requirements like how do you support multiple multi-geo environments in this case. This is where there's yet another project that becomes healthy. It's called Console. So Console is like etcd. It's a distributed key value store. But the important feature that Console has is the ability to kind of set up services in them, which would allow you to locate your actual service where they run, right? So I've talked about Kubernetes service. Now, all I need is like, how do I get my clients to go to the right guy? And so how does the client know where to connect, right? So that's the missing piece that Console brings in. So Console now becomes like your authoritative store saying, where is your service running? So your whole service discovery is now based on clients talking to this guy to get to connect to the right server instance where it is running, right? So this is now what you have. Console itself is distributed, so it runs on multiple nodes, so it's highly available. Kubernetes service is distributed. It runs on highly node. So if you look at the flow of time, there is no single point of time. So typically, how does a client connect to a Postgres server? They have a name. They know a port. They will look up the name in a name server and connect to that port. Now, your name servers are typically replaced by Console. So when you do a name server, it is serviced by Console. Console gives you one of the Kubernetes IP addresses in a round-robin fashion, depending on which one is available with the minimum latencies that you can set. Your now client connects to that Kubernetes server. The Kubernetes service will now take your request and reroute it to your actual container. So this is how you kind of get like a super highly available environment where you make a call, because at the end of the day, like I said, what people want is, I don't care, just give me a name and I'll connect to it, and it's your duty to make it highly available, right? Now, there are things that you need to be aware of. If you're using certificates, you want to create the certificates in the name of the host IP that you're looking into Console. So that way, your server will always be able to do verification based on the name. So I think one of the previous mistakes I've seen is a lot of people are creating certificates based on IP addresses. It shouldn't be done on the IP addresses. It should be done based on the service name that you're going to access to that one. Service name typically would be an FQDN name of how you are looking up that server, right? So a few things that you would look out here is like an interesting feature that I find about console is the ability to do multiple data records. So you can define master and slave separately, but then you can also have a common name which can do round robin across all of them. So like I'm showing you 2 examples out here, right? I don't care, I'm going to do a read query, just take me to anyone. You could use something like my PostgreSQL service domain, look it up and connect to it. But if you want to connect to a specific master, I want to connect to the master, you can set up tags which will point you to the actual master node behind the scenes. And then you can use the master tag to connect to that right node, because you may have five nodes running in master-slave pairs, but if you want to connect to the master one, you can just set the tag as an additional prefix, and it will connect you to the master node. So this kind of now helps you from a client perspective. You're completely hiding the complexity behind the scenes, right? If you look behind the scenes, how many pieces do you have? You have Kubernetes, you have console, you have Petroni, you have etcd, you have Postgres replication, you may have shared storage, you have infrastructure thing. There is a lot of complexity. But now suddenly from a client perspective, all they have is a DNS name and a port. Now, unfortunately, if you look at it, what I have said is I haven't talked about the port yet, right? Because I'm still assuming everything is 5432. There is actually a feature which I want to talk about, but this is kind of like the layout that you have, I mentioned, right? A client looks up on console where the service runs. It gives you a set of IP addresses for your Kubernetes cluster. It goes and connects to that. Based on the port that it's connecting, it will be serviced by the Kubernetes service provider at that point, which will proxy it to your actual node that is running, right? Now, what you want to do at this point of time, what I've talked about is always using 5432. Now, typically what happens is like, we did this with Rackspace. I say, hey, I need one IP address for every service that I run. That way I can, because 5432, that port you can only run on one IP address. And they said, you cannot take any more IP addresses from us unless you now pay us, because they have limited IP addresses in the IPv4 range, so they're going to give us more, right? So one of the things that we kind of ran into problem is like, I can't use 5432 for every service that I want to deploy out, right? Because I want to use kind of like some sort of bin packing, so I don't need that many VMs and that many IP addresses. Like, how do I kind of bring down my infrastructure to a minimum thing? So this is where like you say, maybe your Kubernetes doesn't listen on 5432 anymore. It will listen to maybe a random port, right? Now so that's one of the things that you'll see more and more. Like people are using non-standard ports because they have limitations on how many port number they can run on a specific IP. So this is maybe one enhancement I'm actually just looking into Postgres. So the libpq, so there is a standard called SRV records in name servers. It has been there ever since I know, but I don't think a lot of clients use that. Most people use A records and quad A records to get the hostname resolution to an IP address. But there is an SRV record which not only gives you a hostname, but it also gives you a port to connect to. Now, libpq, the last I looked at it, doesn't support this. That would be a small enhancement, but it would solve out a lot of needs of this complex environment that is going, because I don't want to give 5432 to the same service out there. I want that port to be dynamic. And the dynamism actually comes through the SRV records, where you can define in console this IP and this port, that's where your service runs. Go and connect to that one. And so the record names is slightly different. It's not the standard A or the quad A. It's the SRV, which is the service record. So that's probably an enhancement. I'll probably start a thread on hackers to see what we can do about that. That would help you to even eliminate that you have to mention the port of where your service is running. Because now, all you give out is a service name. It discovers where it runs. It discovers the port it's running on. It goes and connects to it. Your certificates and everything are based on your service names. It will connect to the underlying infrastructure where it runs and service that request out. Right? So that is kind of my summary. So the big thing to do is, whether you like containers or you don't like containers, containers are here to stay. You will see more and more deployments. I do estimate that a lot of new deployments that are going by next year will be moving to some form of the deployments that I talked about. The other thing is container by itself is just a technology. You cannot solve everything with a container. As we talked about, you need a bunch of products technologies to come together to solve your HA needs. One of the things you see is like there are more and more things that are determining the status automatically. I call it as a democratic way of kind of determining who takes over the next master spot. And that thing may be still tweaked, but the good thing is like, that's kind of very isolated in that Patroni layer, and we'll leave that to the experts to tune them up for Postgres, but the rest of your infrastructure doesn't change, right? So you're kind of abstracting out. You now kind of have to just make sure that module works correct, but the rest of the infrastructure doesn't need to change for that. So with that, if you have any other feedback, I didn't take any questions because I didn't have time to finish all the slides right on time, and maybe we can take one or two questions at this point of time. Yeah?
Point of notice, you drew the applications outside the Kubernetes cluster, but if they were inside the Kubernetes cluster.
So typically when they run within the same Kubernetes cluster, there is an internal Sky DNS that reroutes them to the service. There are two ways to define service, internal service or external service. Internal service can actually just use their internal names to get to it. External service typically will have to use their public name to get into it.
And there you could also discover the port.
Yes, yes. So that is actually hidden by containers, because container, what port you expose is what they access and is internally rerouted to the actual port that is running. So most people would still assume I'm talking to 5432 database if you're all running in an internal environment and it will connect to it. The problem comes is when you take your database and your applications and separate them out, then you have to worry about the external port. Yes?
In your multi-geo diagram, how is the data getting replicated?
So there are a couple of ways to do that. Like if you're using some sort of shared storage, you can do the storage vMotion that the underlying storage platform gives you. What the other way you could do is you could use some sort of PG logical if you want to do a replication async way. You could use Postgres cascading slave to get the data out. So there are various ways to get the data onto the secondary geo. In the interest of time, I haven't gone to that way of explaining it out. But yeah, you actually have choices. At some point of time, I would say even that part can be automated. So you can actually say, hey, do that deployment with a spare delayed copy into a DR, and then you can actually solve that problem also. Yeah?
Now the Kubernetes, can be used for distributed technology, like distributed databases?
Yes, it can. Yeah. In fact, it's actually more harder for technologies like master and slave deployments. For distributed technology, it is great. Like if you use something like Mongo, where your query can go to any node and it is able to write, the replica sets is very easy. It doesn't have to worry and do specific things. For master-slave, there is actually a hard thing you have to do is like, how do you make sure it all writes go to the master? So the master-slave architecture actually makes it harder for Kubernetes. Like the deployments are actually more harder.
How many kind of databases will get support like this? Just Postgres or any other database?
So this deployment, what I talked about, is not very specific to Postgres. You can actually do that for MySQL, Oracle, and other things. The replication technologies will change with each database, but I think that your enterprise infrastructure doesn't need to change for that.
I just want to comment, if you want to see an example of how to handle master-slave databases under Kubernetes, take a look at my talk recording from yesterday.
Yeah. Any other questions? Okay, cool. Thank you.